Good morning, students. In this video, I'll discuss about periodic properties. What are these periodic properties? There are some important periodic properties like atomic size, metallic character, non-metallic character, ionization potential, or it also called ionization energy, electron affinity, electronegativity. These are some properties. These are some properties which are called periodic properties because these properties show a regular variation or gradation in periodic table. Okay, so what are periodic properties? The properties of elements which are directly or indirectly related to electronic configuration. The properties of element which are directly or indirectly related to their electronic configuration. So a regular gradation or regular variation as we move across a period or from left to right or down the groove. Okay, from top to bottom, and these properties are known as periodic properties. Okay, so properties which are directly or indirectly related to electronic configuration and so a regular variation across a period or down a groove are known as periodic properties. And the main important periodic properties are atomic size, metallic character, non-metallic character, ionization energy, electron affinity, and electronegativity. Okay, so first periodic property is atomic size of atom. Okay, so what is atomic size or radius of atom or atomic radius? It is the distance between the center of the nucleus of an atom and its outermost shell. Atomic size means it is distance between the center of nucleus. It is the distance between center of nucleus and the outermost shell. Okay, this is the atomic radius, and larger the value of atomic radius, larger is the size of the atom. Now see the factors. Atomic size depends upon two factors. One is number of cell, another is nuclear charge. So on which factors atomic size depends? Answer is nuclear number of cell and nuclear charge. So first, number of cell. Okay, so first factor is number of cell. How the number of cell determine the size of an atom? Okay, so an increase in the number of cell increases the size of atom. Very simple. An increase in the number of cell increases the size of atom because the distance between the outermost cell and nucleus increases. Okay, so here is the value of number of cell, larger is the atomic radius. Okay, and second factor is nuclear charge. Nuclear charge means positive charge in the nucleus. Okay, so nuclear charge, it is the positive charge present in the nucleus, that is number of protons. It indicates generally it indicates the number of proton. Nuclear charge means number of proton. Okay, so nuclear charge is the positive charge present in the nucleus of an atom, which is equal to the number of protons in the nucleus, that is atomic number. Nuclear charge means atomic number. And an increase in nuclear charge decreases the size of atom. Why? An increase in nuclear charge decreases the size of atom. This is because the electron are negatively charged and nucleus is positively charged. Okay, due to presence of proton in the nucleus. And an increase in nuclear charge, that is an increase in the number of protons, decreases the size of atom. This is because the electrons are then attracted toward nucleus with a greater force. Okay, this is because the electrons in the outermost shell, electrons are then attracted toward the nucleus with a greater force. thereby bringing the outermost shell closer to the nucleus. So an increase in nuclear charge decreases the size of atom, and with increasing number of cell increases the size of atom. Now see or variation or trends in atomic size unpredictable. Trends in atomic size or atomic radius. So first, down a group. In a group, the size of atom in a group the size of an atom increases as one proceed from top to bottom. You have to remember this line. The variation in atomic radius in a particular group. In a group, the size of an atom increases as one proceeds from top to bottom. And this is due to the successive addition of cell. This is due to the successive addition of cell. Okay, down the group, number of cell increases, so size of atom increases. Okay, so in a group, the size of an atom increases as one proceeds from top to bottom, and this is due to successive addition of cell as one move from one period to the next period in a group. For example, in case of group 1, the elements are group 1 elements are hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. These are group 1 element. You can see in group hydrogen only one atomic number is 1, only one electron, so electronic configuration is in k cell 1 electron. So in hydrogen only one cell is there. In case of lithium, atomic number is 3, so electronic configuration is 2 comma 1. Case in k cell 2 electron and in l cell 1 electron. So lithium has 2 cell. And sodium, atomic number 11, sodium electronic configuration 281, and sodium has 3 cell, k cell, l cell and m cell. Okay, so similarly in potassium, atomic number 19, potassium has total 4 cell and electronic configuration is 2881, k cell, l cell, m cell and k, l, m and n. These 4 cells are exist in potassium. Okay, so it is clear from this the potassium, rubidium, cesium and francium, up to cesium it is given. Down the group, number of cell increases. Okay, that's why size of atom increases down the group. Similarly in group 17, the elements are fluorine, chlorine, bromine, iodine, astatine. Okay, and down the group size of atom increases, that is fluorine less than chlorine, less than bromine, less than iodine, less than astatine. Okay, because down the group new cell are added. Now see across a period, change in atomic size across a period, that is from left to right. In a period, the size of an atom decreases from left to right. In a group, from top to bottom size increases, while in a particular period, the size of an atom decreases from left to right. This is because the nuclear charge, here the factor is nuclear charge. This is because the nuclear charge, that is atomic number, increases from left to right in the same period, thereby bringing that outermost cell closer to the nucleus, and therefore in the second period it has been found that lithium has the largest atomic size and fluorine has the smallest atomic size in second period. Okay, and you have to remember that across the period no new cell are added. Okay, so lithium has 2 cell, similarly beryllium has 2 cell, boron also has 2 cell, carbon, nitrogen, oxygen, fluorine, all these elements of second period, these are elements of second period, all these elements have 2 cell. But from left to right, from lithium to fluorine, atomic number increases, so nuclear charge increases. Okay, and force of attraction between the nucleus and outermost cell increases. Therefore size of atom decreases from left to right across a period. Okay, so size of lithium is less than, so you can write size of lithium is less than size of beryllium, less than size of boron, less than so, sorry, just opposite. Lithium is the largest though, so size of lithium is greater than size of beryllium, greater than size of boron, greater than size of carbon, greater than size of nitrogen, greater than oxygen, like this. Okay, so in second period the lithium has the largest atomic size and fluorine has the smallest atomic size. Okay, you can see from this one also, lithium is largest and fluorine is the smallest. Okay, and one thing I want to mention you, the group 1 element fluorine chlorine, these are the group 17 element, that is atomic size decreases from group 1 to group 17 across a period, but group 18 elements, that is noble gases, they have uh, uh, they have largest atomic size than group 17 element. Okay, this is the exceptional case. Similarly, in third period, the elements are sodium, magnesium, aluminium, silicon, phosphorus, sulfur, and chlorine. These are third period element, and uh, you know that across the period from left to right, size decreases. So sodium in third period, sodium is the largest. Sodium atom is largest, and chlorine atom is smallest in third period. In second period, lithium is largest and fluorine is smallest in second period, and in third period sodium is largest, so and chlorine is smallest. Okay, now see here it is written, and as an exception the size of the atoms of inert gases are bigger. This is because the outer shell of inert gases are completed. Okay, and they have the maximum number of electrons in their outermost shell. Thus the electronic repulsion are maximum in outermost shell in case of noble gases. Hence the size of the atom of noble gases are bigger. Okay, now here it is given size of cation and size of anion. You know, cations are formed by losing electron and anions are formed by gaining electron. Okay, when an atom loses one or more electron, they form cation, and cation has smaller size than anion and than neutral atom. Okay, so cation is formed by loss of electrons. Hence protons are, after losing electron in the nucleus, you will see that in the nucleus there will be number of proton will be high compared to number of electrons. So cation is formed by loss of electrons, hence protons are more than electrons in a cation. So electrons are strongly attracted by the nucleus and pulled inward, and hence size decreases. So size of size of cation is less than size of neutral atom. So size of sodium plus ion, Na plus ion, is smaller than sodium atom. Now size of anion are formed by gaining electron. So anion is formed by gain of one or more electrons. Okay, and number of electrons are more in case of anion. Number of electrons in case of anion, the number of electrons are more than the number of protons in the nucleus. So effective positive charge in the nucleus is less, so less inward pull is experienced. Hence the size expands. So size of anion is more than size of neutral atom. For example, when chlorine atom accept one electron, it forms Cl minus ion. Okay, and chlorine ion has bigger size than chlorine atom. And now see size of isoelectric electronic ions. Isoelectronic ions means ions having the same number of electrons. Ions having the same number of electrons, like Na plus, Mg2 plus, F minus, O2 minus, all these elements, all these ions have same number of electrons. that is 10 electrons. So these are isoelectric ions. And now see size of isoelectric ion. The ions having the same number of electrons depends upon the nuclear charge, that is number of proton, and greater the nuclear charge, that is nuclear pull, get as smaller is the size. Okay, and you know that cation has smaller size than neutral atom, and anion has higher size or bigger size than neutral atom. Okay, in magnesium 2 plus Na plus F minus O2 minus, in all cases only 10 electrons are there, so number of electrons are same. And now count number of protons. In magnesium 2 plus number of protons are 12. In sodium plus ion number of protons 11. In F minus number of proton is 9, and in O2 minus number of proton is 8. So size of uh, magnesium 2 plus is less than, as the number of proton, that is nuclear charge, is high in Mg2 plus. So size of Mg2 plus is less than Na plus, and size of Na plus is less than F minus, and size of F minus is less than O2 minus. Okay, next property is metallic property. Metallic property, metallic property those elements which have a tendency to lose their valence electron, those elements which have a tendency to lose their valence electron and form a positive ion, they are considered as metal. Okay, so those elements which can lose their valence electron easily, they are mainly metallic in nature. Okay, and they are, after losing electron, they generally form cation. So for example, when sodium atom loses one electron, it forms Na plus. Mg2 magnesium, when loses two electrons, it forms Mg2 plus. Okay, and metallic character metallic character also depends on two factor: atomic size and nuclear charge. Okay, and those elements which can lose their valence electron, they are most metallic in nature. You have to remember this point. So as the atomic size increases down the group, atomic size increases, force of attraction between the nucleus and outermost shell decreases. So uh, so metallic character increases down the group, and across the period, no, size decreases. So size decreases means force of attraction between the nucleus and outermost shell increases, so metallic character decreases from left to right. So atomic size and nuclear charge, these are two factors which determine the metallic character of elements. So nuclear charge, the greater the nuclear charge, the greater is the force of attraction between the nucleus and outermost electron, and this makes it difficult to remove the electron from the outermost orbit. Thus metallic character or metallic nature decreases as nuclear charge increases. And you have to remember that metals are generally have one, two, or three electrons in their valence shell. Metals, they have generally one, two, or three valence electrons, that is with one, two, or three electrons in the valence shell. And metals, they can lose their electrons, valence electron, easily. Okay, and metals are generally reducing in agent, because they can lose electrons to complete their octet. That's why they are reducing agent also. So metals are good reducing agent. Greater the tendency to lose electrons, get stronger is the reducing agent. Now see trends in metallic character, that is variation in metallic character in predictable. So first, down a groove. Okay, on moving down a groove, the atomic size increases, and hence nuclear charge also increases, and the effect of an increased atomic size is greater compared to the increased nuclear charge. Therefore the tendency to lose electron increases down a group, because atomic size increases. Okay, and elements can lose electron easily. So thus metallic character or metallic nature increases as one moves down a group. Okay, so remember, down a group metallic character of element, down a group metallic character of element increases. Okay, you can see here it is given in first period, in first group, that is group 1, lithium to cesium metallic character increases. Okay, because size increases, force of attraction between nucleus and outermost electron decreases, and the elements can lose their electron easily. Okay, so in group 1, lithium, sodium, potassium, rubidium and cesium, down the groups size increases, metallic character also increases. So cesium has uh, highest metallic character. Okay, so in group 1, lithium is least metallic element, and cesium is the most metallic element. Here one note is given why francium is not most metallic element. This is because francium is radioactive, so its properties are not known. So you have to say that cesium is the uh, most metallic in nature in group 1, because the francium is radioactive and its properties are not known. And now see, across a period, that is, on moving across a period from left to right, across a period, that is from left to right, the nuclear charge increases, size also, atomic size decreases. Okay, in a particular period from left to right, atomic size decreases, and element cannot lose electrons easily. So the metallic nature decreases across a period moving from left to right. Metallic nature decreases across a period moving from left to right. For example, in second period, that is, the elements of second period are lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. These are second period element. There are total seven period, you know. And in this, these are second period element: lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. And lithium and beryllium, these are metallic in nature. Boron is metalloid, and carbon, nitrogen, oxygen, fluorine, these are non-metal. So from left to right, metallic character decreases, non-metallic character increases. Okay, so in second period, lithium is the most metallic in nature in second period, and in first group, lithium is the least metallic in nature, because down the group, metallic character increases, and across a period from left to right, metallic character decreases, non-metallic character increases. So metallic character also decreases in third period also. Okay, and in third period, sodium is the most metallic element. This is the third period element. uh, Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine and argon. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine and argon. And in third period, sodium is most metallic, and chlorine is argon is least metallic in nature. Okay, from left to right, metallic character decreases. Here it is also given, you can see sodium and magnesium and aluminum, group 1, group 2, group 3, these elements are metal. And group 14, that is carbon group, silicon is metalloid, and phosphorus, sulfur, chlorine, argon, these are non-metals. Now see, non-metallic character, just opposite of metallic character. Okay, the element which have a tendency to gain electron, the element which have a tendency to gain electrons in order to attain octet in their outermost orbit are considered as non-metals. So non-metals, they can gain electron easily, and metals can lose their electrons. Generally non-metals, they have 5, 4, 6 or 7 electrons in their outermost shell. Okay, so non-metals usually have 5, 6 or 7 electrons in their outermost shell, while metals have 1, 2 or 3 electrons in their outermost shell. Okay, so non-metal usually have 5, 6 or 7 electron in their outermost shell, and they can gain 3, 2 or 1 electrons respectively in order to attain octet. Okay, for example, chlorine, oxygen. these are non-metal, and they can accept they gain one and two electrons respectively to form anion. Chlorine accept one electron to form Cl minus ion, and Cl minus is more stable than Cl chlorine atom. This is because in Cl minus ion their outermost shell is in the outermost shell 8 electrons are there in Cl minus, so Cl minus ion is more stable than Cl because 8 electrons are present in the outermost shell of Cl minus. Similarly, oxygen, which has electronic configuration 2 and 6 2 6, so it accept 2 electron to become O2 minus. Oxygen accept 2 electron to become O2 minus, which have 8 electrons in the outermost shell. So O2 minus is more stable than oxygen. And non-metallic character also depends on atomic size, nuclear charge. Okay. First point is atomic size. Smaller the atomic size, greater is the nuclear pool, and the tendency to gain electrons increases. Therefore, elements is more non-metallic in nature. Smaller the atomic size, greater is the non-metallic character. Okay, and nuclear charge, greater the nuclear charge, greater is the tendency to gain electron. Hence, more non-metallic in is the element. Okay, greater is the tendency to gain electrons. Hence, more non-metallic in is the element. Okay, now see trends in non-metallic character. Trends or variation in non-metallic character. Down a group, just opposite of metallic character. Down a group, atomic size increases due to addition of down a group. Atomic size increases due to addition of new cell. Okay, and down a group and nuclear charge down a group size increases, and due to increase in atomic size, non-metallic character decreases down the group. Okay, due to increase in atomic size, tendency to gain electron decreases, and therefore non-metallic nature decreases down a group. For example, in group 14, you can see group 14 elements are carbon, silicon, germanium, tin and lead. The group 14 elements are carbon, silicon, germanium Ge, and tin means Sn, and lead means Pb. Okay, so in this group you can see carbon and carbon is non-metal. Silicon and germanium are metalloid. They have the properties of both metal and non-metal. And tin and Pb, that is tin and lead, they are metal. Okay, so down the group, non-metallic character decreases but metallic character increases. Non-metallic character just the opposite of metallic character, you have to remember this one. And across a period, that is from left to right, on moving across a period, size decreases, so uh, tendency of gaining electron increases. So non-metallic character increases across a period. Across a periods Across the period, non-metallic character increases from left to right. For example, in third period, and the third period elements are sodium, magnesium, aluminium, silicon, phosphorus, sulfur and chlorine. These are third period elements: sodium, magnesium, aluminium, silicon, phosphorus, sulfur and chlorine. And you know atomic size decreases from sodium to chlorine. So non-metallic character increases. So non-metallic these element, that is phosphorus, sulfur, chlorine, these are non-metal, and sodium, magnesium, aluminium, these are metal, and silicon is metalloid. So from left to right, in a particular group period, across a period, metallic character decreases and non-metallic character increases. Okay, metallic character decreases and non-metallic character increases in a particular group. And and non-metals, like metals, are reducing agent because they can gain electron. Okay, while non-metals are oxidizing agent because they can lose no sorry metals are reducing agent because they can lose electrons, while non-metals are oxidizing agent because they can accept electron. And now see nature of oxide also show periodicity. Okay. So across the period, the oxide of different elements show a variation in their properties. Okay, so the oxide of element in a particular period decreasing basic nature and finally become acidic. For example, in case of third period elements, in case of oxide of third period elements, that is oxide of sodium, magnesium, aluminium, silicon, phosphorus, sulfur and chlorine, that is Na2O, MgO, Al2O3, SiO2, P2O5, SO3, Cl2O7. These are oxide of third period elements. And from left to right, the basic character decreases and acidic character increases. Thus, Cl2O7 is most acidic and Na2O, sodium monoxide, is strongly basic in nature. Okay. So from left to right, across a particular period, for oxide of group for oxide of group for oxide of period 2, period 3, oxide of this period, the basic nature from left to right decreases, acidic nature increases, and down the group basic nature of oxide of metal increases. Down the group basic nature increases and acidic nature decreases. Now see next periodic properties, chemical reactivity. The reactivity of element depends their tendency to lose or gain electrons to complete their outermost orbit. The chemical reactivity of elements the chemical reactivity of elements depends upon their tendency to lose or gain electrons to complete their outermost orbit. Greater the tendency to lose electrons, greater is the reactivity in the case of metals. Similarly, greater the tendency to gain electrons, greater is the reactivity of non-metals. Okay, and trends in chemical reactivity across a period. On moving from left to right in a period, the chemical reactivity of element first decreases and then increases. On moving from left to right in a period, the chemical reactivity of element first decreases and then increases. Okay. So you can see third period elements: sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. And sodium is the most reactive metal and chlorine is the most reactive non-metal. This is in third period. In second period, lithium is the most reactive metal and fluorine is the most non-metal in second period. Okay. So reactivity across a period first decreases and then increases. In third period, silicon is the less reactive. Okay, so first reactivity decreases and then again increases. And down the group, the tendency of losing electrons increases down the group, since chemical reactivity in metals depends upon the tendency to lose electrons. Thus, reactivity increases down the group. Chemical reactivity of element increases down the group because tendency to lose electron down the group increases. So, most reactive metal is at the bottom of group 1. That is, you can say it is cesium. Actually, francium is the last element, but as francium is radioactive, its properties are not known. That's why you can say cesium is the most reactive metal. Okay, and chemical reactivity of non-metal decreases on going down the group, as it depends upon the tendency to gain electrons, and which decreases down the group. So for most reactive non-metal is at the top of group 17, and the most reactive non-metal is fluorine. Okay, now see some physical properties. Gradation in some physical properties are also given, and in Einstein energy electronegativity. This periodic property I'll explain in the next class. Okay, and some defined physical properties and their gradation also given. For example, melting point and boiling point of metal. Melting point of boiling and boiling point of metal decreases going down the group. Okay, for example, lithium, sodium and potassium. Lithium to sodium to potassium, melting point and boiling point decreases. So melting point and boiling point decreases are down a group. You have to remember this one. Okay, and for non-metal, this is for the metal, lithium, sodium, potassium, and for non-metal, melting point and boiling point of non-metal increases down down the group. Melting point and boiling point for non-metal increases down the group. For example, fluorine, chlorine, bromine, iodine, these are group 17 element, and melting point, boiling point increases from fluorine to chlorine, chlorine to bromine, bromine to iodine. Okay, and one note is given here: across the period left to right, that is left to right, melting point and boiling point usually increases up to group 14 and then again decreases. Melting point and boiling point across a period, that is from left to right, melting point and boiling point usually increases up to group 14 and then decreases. Okay, and these properties are not important: melting point, boiling point, density also given, atomic size is important, metallic character, non-metallic character, their chemical reactivity important, and electronegativity, ionization energy, these are most important periodic property. Okay, and density, melting point, boiling point, these are not important. Okay, so density of element across the period increases gradually to maximum and then slight decrease may be noticed, and down a group density of element increases gradually. Okay, thank you student.